All right. Come in, sit down. Welcome everybody to HOTRFC at IETF 125. We have 16 speakers here, and I am reliably informed that at least one of them is not talking about AI. All right, shall we skip through the compulsory slides? These are the rules. They apply even in this session. The note well is in force, so note it well. You're going to see this a lot of times throughout this coming week. So if you read one word in each session, you will have read the whole thing by the end. All right. If you want help with some new work, whether you're one of the 16 people here or anything else, there's a new work help desk. There's a couple of times that this will be right outside in the registration area, so you already know how to find it. All right, so the rules of HOTRFC. This is where you make a request for, I'm just going to read this. Oh, it's down there. It's a good way to find people to talk to, and this is where you find collaborators, where you find supporters, where you find someone to review your work, hopefully. Everyone gets 4 minutes from the start of their time to the end. There's 16 of them, so plenty of people. That means we're going to be pretty strict. We'll set a timer. When we get to the end, the please applaud slide is going to appear, and you are going to applaud so loudly that they can't keep talking, and they leave happy with what they've achieved in that 4 minutes. There's no questions here. You can ask follow-up questions from people outside. If you do want to ask follow-up questions straight away, go outside too, so the next speaker is not being overridden by them. We're using Data Tracker. We don't force people to log in for this one, do we? Because they're not asking questions. Yep, all the slides are in Data Tracker. You can go read them later. All right. Now this is your chance to practice. Applaud, please. That was okay, but I think we can do better. So I'm just going to rewind. 3, 2, 1, go. Oh yeah! That is how it's done. All right, thank you. And with that, I believe we are on to our very first speaker. So come on up. Yeah, thank you, please. The only time not to applaud is when they're actually speaking. You can keep clapping the whole rest of the time.
Okay. Hi, everyone. I'm Jingyang Li, and this is Xiaoyi Yang. We're coming from Huawei, and today we want to talk about 2 practical problems in multi-agent collaboration, and our proposal about how to fix them. Imagine an OS-level system agent on your phone orchestrating multiple app agents, travel planning, media processing, and everything is automated, no friction. That's our vision, right? But the reality is harder. Terminal face strict limits on tokens, batteries, and latency. The current protocol like A2A and MCP were not built for this. 2 problems keep coming up. The first is context fragmentation. Fragmentation. Just imagine status, plain text exchange cause massive token overhead and execution failures. And the second is ORC fraction, reactive concerned prompts, break workflows, and exhaust users. So here we have 2 proposals. Yeah. The first one is when an OS agent coordinates across maps, weather, and the booking agents. Today, every handoff resends everything from scratch. No shared task state, no dependency tracking, and a very high overhead, a very high latency, and the text losses. So our fix is replace the plain text exchange with a structured semantic schema that natively track context boundaries, dependency, and execution states. And the work is detailed in our first draft.
Okay, and for authorization, MCP handles OAuth 2 reactively. A simple email plus calendar workflow triggers separate consent promotes multiple times mid-execution. And thus, consent fatigue, and broken automation. So our fix is record security requirements upfront in resource metadata, aggregate all required scopes, and fire one single authorization flow before execution begins. That's our second, and that's our second draft. Please see more details in our draft. And for summary, terminals are constrained. Today's stateless reactive protocols cannot support complex multi-agent workflows. So we are proposing a shift to protocols that are structured, stateful, and pre-authority. We are here for feedback. Catch me after this session or send our email. Thank you.
Thank you. All right. Our next speaker on knowledge graph for network management. Do we have Ming Jie?
Yes.
Cool. Okay.
Okay, everyone, I'm Ming Jie from Zhongguancun Lab. The topic I'd like to share with you is about using knowledge graph to assist network management. The network data is facing some challenges, including the the data overload. For example, the network analysis is becoming more complex by its high volume data with complex correlations. And the second challenge is the vendor-specific silos, such as the Young model describes the same concept, but with different structures and syntax. And the data heterogeneity also increases the difficulty in correlating the diverse operational data like the configurations and logs. To tackle these challenges, several knowledge graph drafts have been proposed at the NMOP working group, but they are discussing about how to define and construct the knowledge graph. In this set, we want to discuss more about how to use knowledge graph. Given well-constructed knowledge graphs, the engineers should interact with the knowledge graph with some structured query language, like the Cipher. But it will introducing higher learning barrier, and the graph and the Young schema is continuous evolving, and we need to translate the abstracted intent to some actionable query language. So we want to introduce an intelligent interface. It can converting human intent natural language or domain-specific language to queries. And it can unify the heterogeneous inputs and ensure the security and campaigns, and ensure the acute translation from the intent to query, and finally synthesize the query results. This framework consists of 3 layers. The first is the input and the interaction layer. The second is the unified internet gateway. The final one is the data and knowledge layer. For the input and interaction layer, it can receive 2 types of input. The first is natural language. The operators can describe their intent with the natural language. The second is the domain-specific language. And this interface is responsible for providing a unified APIs and deliver the queried results to the user. And for the unified internet gateway, it first receives the incoming request. Then it performs some necessary authorization, and then it passes the intent into intermediate results and intermediate representation, and then generates the actionable graph query language. For in the last layer, for the graph database layer, it is responsible for execute the query language and return the derived results. Here are some use cases. For example, operator maybe want to investigate is if the server is detected by IETF flood. He can describe his intent and generate the cipher language and return the results. Here is another use case. We also launched the Hexen project, so we build a network graph and provide a retrieval interface that where users can use the natural language to.
Thank you. All right.
Hello everyone, my name is Ke Liu and I'm come from China Mobile. And today I'm going to introduce the use cases for alternative marking for the lost location in per-packet load balancing networks. Many per-packet network load balancing schemes have been proposed to achieve near optimal network performance. For example, NVIDIA adaptive routing, Broadcom dynamic load balancing, global load balancing, and China Mobile global scheduled Ethernet. These schemes split packets onto parallel passes to eliminate load imbalance. However, packet splitting brings many challenges for lost location. In flow-based networks, packets with the same fab tuple will traverse the same network passes. While in packet splitting networks, packets with the same fab tuple may traverse different passes, and replacing the dropped packets for lost location can result in incorrect conclusions. So packet splitting networks require real-time loss detection and location on switches. And alternate packet marking is an efficient way for switches to precisely locate loss in real time. And this slide introduces the workflow of alternate packet marking. Firstly, packets are periodically and ordinarily marked at the traffic entry points, such as the source network interface cards or the source top rack switches. And secondly, in each period, each switch calculates the difference between the ingress and egress packet counts in the previous period. This step is to accurately determine the total packet loss count. And the alternate marking ensures that the packet count in the last marking period remains unchanged. This allows for an accurate loss counting. And this method can accurately detect nearly all packet loss in switching, include silent packet loss. Yeah. Note that the silent packet loss cannot be detected by the traditional switch loss count. Yeah. And this slide shows the three use cases in per-packet load balancing networks. And the first use case is to use alternate marking to monitor all packet loss on switches. And by marking all packets alternately, we can accurately detect all packet loss in the switching process. And this method enables precise switch loss rate monitoring for every switch in the cluster. And with these metrics, we can monitor the abnormal switch. Yeah. The second use case is to monitor packet loss for loss-sensitive services. Not all the services are sensitive to packet losses. Some services are highly sensitive to packet losses, such as AI training and AI inference. And these services has very severe barrier effect. Yeah. While other services are not maybe not loss sensitive. Yeah. So for the loss sensitive services, we need to focus on every loss event. While for the services that are not sensitive to loss, we need only to focus on the severe loss events. Yeah. So by merely marking packets in loss-sensitive services, we can focus on packet loss events only in loss-sensitive services. And the last use case is to locate packet loss in network propping system. Yeah. By marking props alternately, we can accurately locate prop loss, and we can locate the anomalous switches. Yeah. And that's all for my today's presentation. Yeah. Thank you. Hello, everyone. I'm Wang Zan from Professor Cui Yong's group at Tsinghua University. Today, I will present our project, Open Gateway. It's an open source agent gateway for cross-domain collaborations. Oh.
Is it? Oh,
Other way.
the other way. Other way. Other arrow.
Oh, okay. First, let us say why an agent gateway is needed. Today, many real-world tasks need multiple agents to work together to solve a complex task. For example, this happens in DDoS defense, conference traveling, and smart factories. These scenarios have common challenges, like heterogeneous agents and complex tasks. We also look at the existing gateways products. They already provided useful capabilities, but there are still gaps for our targeted scenarios. Some products doesn't support general connection between heterogeneous agents. Some are more focused on connection control than organization. So we proposed our solution, Open Gateway. It has 4 main parts. The first part is heterogeneous connectivity. The problem is that the different tools and agents often use different protocols and interfaces. This makes connection and collaboration difficult. Our systems suppose capacity registration and automatic proto translation. And the second part is task orchestration. In long and complex tasks, one-shot generation is often unstable. This is because there is dependencies, tool constraints, and uncertain in steps. Our approach is to support replanning with feedback and routing by vectorized agent profile. And the third part is working memory. In long horizon tasks, the system may accumulate too much temporary information. This can lead to circular logic and loss of focus. We use zoned short-term memory to maintain agent's status, and we also use KV cache to avoid redundant computation. Okay. Oh, okay. The fourth part is a security assurance. The security risk include untrusted inputs over permissioned actions and memory commutations. Our approach include pre-execution compatibility assessment and heartbeat monitoring during execution. We also support sensitive information guarding and rewriting. And for deployment, Open Gateway is designed for edge servers and cross-domain enterprise services. It supports private protection, local model, and external APIs. We also expect it have a better efficiency and a lower token cost. Right now, Open Gateway is an open source project on GitHub. Task orchestration and working memory are already to use. More functions are coming soon. We have published the code on GitHub and submit the active IETF draft. We welcome more people to join us. Thank you. Thank you for your listening.
Hi. Hello from remote space. I'm Nick Sullivan, and this is SAFE, Field Algorithm Flexible Envelope. SAFE is an encrypted container for large file that combines multi-recipient keying, multi-factor credentials, and random access authenticated encryption. The goal is to make one format that works for modern encrypted data handling without forcing a trade-off between performance, flexibility, and cryptographic structure. Next slide, please. The motivating gap here is simple. Today's formats do some of these things well, but not all of them natively combine large file framing, streaming decryption, random access reads and writes, multi-factor recipient unlock, and algorithm agility all in one place. SAFE is an attempt to fill that gap with one container format that's designed from the start for large files, multiple recipients, and all these sort of things, as well as cryptographic evolution over time. Next slide, please. The core abstraction here, it might be hard to read, but the slides are available, is the lock. Each lock independently wraps a content encryption key, and any one lock is sufficient to decrypt the file. That means that you can have one recipient path that is simple, like one HPKE X25519 key. You could have another one that combines an elliptic curve and a password, and you could have another one that combines a post-quantum key with a classical key and a WebAuthn PRF, such as a passkey. The important point here is that the format does not need a special mechanism for every one of the combinations. It composes them through a simple step model inside each lock. And this is what gets you multi-recipient access, multi-factor unlock, and algorithm agility all in one framework. It also gives you a clean path to post-quantum and hybrid deployments without changing the container format itself. And if you want key privacy, identifiers can be omitted, so decryption works by trial rather than explicit labeling. Next slide, please. The second big idea in this draft is RAAE, which is Random Access Authenticated Encryption. This extends a protocol called Stream with per block AEAD. There's a lot of acronyms here, but in any case, it extends the streaming protocol so that you can seek to a block, read it, or rewrite it without decrypting or rekeying the rest of the file. And this matters if the encrypted object is large and you don't want a tiny change to force a full rewrite. Integrity across all seeks is handled with a snapshot accumulator. So SAFE is not just a transport envelope, it's designed for encrypted data that may need selective reads and in-place updates. The deck points to a formal analysis of the definition of this RAAE construction as part of the basis for this design. Next slide, please. So on the wire, SAFE separates ciphertext from framing. There are 3 data section encodings that are currently defined. First is an armored mode, which is a text-safe encoding that works in email, config files, CLI pipelines, and yes, agent-to-agent communication. Secondly, there's a binary linear format, which is the straightforward streaming profile. And the third is a binary aligned format, which is a minimal editing profile where metadata is front-loaded and padded so you can seek directly and rewrite that block and only interact with certain things. Next slide, please. All right, so this is meant to be a practical system, not just a format sketch. This shows 2 concrete format profiles. One is a FIPS-oriented profile, and another is a high-performance one using modern cryptography. There are ongoing cross-protocol implementations. Next slide, please. All right, so the claim is not SAFE replaces every existing format. If you're building encrypted storage, large file formats, agent tooling, or anything that needs rewritable encrypted containers, please reach out to me. Thanks.
All right, thank you. Please be careful out there in this darkened room.
Hello everyone, I'm Yihan from Zhongguancun Laboratory. Now let me introduce our draft AI agent discovery and invocation protocol. Now let me introduce the model vision about why we need added AI agent everywhere in our world, from translation to summarization or the code generation. But every framework has its own API. Integrating agents across platform means writing custom code for each one. There is no standard way to discover or invoke agents. It may have 3 main problems. The first one, platform silos and high integration costs and no interoperability. Now let me introduce the 4 core components about ADIP. The first one is agent metadata stack, standard JSON schema describing any agent capabilities, endpoints, and so on. Think of it machine readable business card for agents. The second one is discovery mechanism, agent register with a registry. Both modes can be combined in one request. The third part, invocation interface, we use HTTP post and JSON to write the field. And the final one is security framework. We use OAuth2 API keys and TLS for authorization. And now is the system architecture. First, the agent register in agent registry. Then a client search the agent from the discover service is the agent registry. Then the registry send the result back to the candidate. And the fourth step is client invokes AI agent. Then the final step is AI agent's response. And in overdraft, we have two optional parts. The semantic routing platform and the gateway. Now is the detail about agent metadata and discover mechanism. The metadata fields include ID, name, capabilities, text, and so on. And the attribute filter and the semantic NL search is I have said that the two ways about discover mechanism. And in our draft version 01, we have a new part about agent semantic resolution. It solves the problem which agent is best suited for the specific task right now. This use case about summarize an English legal document to Chinese. First, we search it and then selected which agent is suitable, and then invoke the agent. And finally respond. We have solved the 5 problems. The first, unified agent metadata, and then 2 more discovery, and uniform invocation interface, and agent semantic resolution ASR. Finally, we concerned about the security framework, and we hope the discussion with us to let our protocol better. Thank you.
All right, we have long-term persistence of attacker infrastructure. Come on up. Yeah.
Okay. Hello, everyone, and my name is Yuan Zhou, and I'm from University College London. And today I want to share you with a very initial results and a very short talk about the long-term persistence of attacker infrastructure across its DNS intelligence and honeypot observations. And so here is the general motivation for this work. So initially, we are trying to do the measurement on the security different layers. And so we have these 2 different sources. And so firstly, we have this very large honeypot collection supported by the Global Cyber Alliance. And also we have another DNS threat intelligence that is supported by the Infoblox. So with these 2 enrichment, we are going to have this attacker behavior and also have the infrastructure reputation at the same time. So the security system observes the attacker infrastructure from the different perspectives. In this case, the honeypot captures the interaction behavior, while the DNS security threat intelligence captures the infrastructure roles. So the aim is to understand the persistent attack infrastructure. And so here is a result from the threat intelligence side, which is going to show the attacker infrastructure persistence. Our observation period is around 16 months, but the lifetime of the persistence in the system is going to be longer, which could be over 10 years. And so the initial funding is that the most attacker infrastructure is short-lived, and however, there are very small fraction persists for very long periods. And we also noticed that there is another phenomenon like this IP address may be used for the mailing list at the initial stage, but after several months, it may change to a web service. So we do such measurement based on this row entropy, where we found the infrastructure ecosystem becomes more functionally diverse. So the more infrastructure roles emerge over time. And this is the funding from the honeypot wheel, which is going to show their behavior. So we do such evaluation in 2 different dimensions. The first one is from the unique behavior patterns, and the other is to check their reuse ratio. So this is going to separately to clearly show the separation of 3 different regions. And so what we found in general is that the persistent infrastructure exhibits different behaviors. So they could have some automated scanners, which shows the repeated simple behavior. And also we have some semi-automated attackers, which seems to be the botnet scripts, exploration frameworks, and also the most complex one, which is going to be the interactive attackers, and which could have some manual sessions and some command execution. And so the key takeaways here with this initial finding is a small number of infrastructure nodes drive many attacks, and this long-lived infrastructure may evade this detection if the threat in intelligence visibility is too short. And also we found that combining these 2 different sources could actually provide a richer view to see different levels of these attackers. And so we are actually looking for the feedback and the discussion with researchers and operators working on the DNS abuse, internet measurement, and the attack infrastructure, and also open for anyone interested in this topic. So I'm happy to take any questions and discussion afterwards. Thank you.
Thank you. We're very classy here.
Oh my God. Give me a second. Hi. So, hi, I'm Henk. Yeah, unfortunately, we are on the hype train here. That's a problem. Verifiable agent conversation records. What does that mean? At least 2 entities talk to agents. It's humans, agents, or mixed as a third alternative. There are a few authors here. It's me, I'm presenting. I'm Henk. Tobias, our AI agentic expert, and Ori doesn't like to be called the verifiable credential expert, so I will not call him that. And so what we're doing, there's a problem. We have agents. Agents communicate. It's very obvious. There are a lot of records for these communications. They are all claiming to have done something, and then they're actually doing something, and then the auditor has no idea what happened because this all is gone, because this happened in a very short time frame. So you don't only have the chain of thought, you have all these conversations. We call them convos right now. I think verifiable agent conversation records is a mouthful. Yeah, please improve on that, bash that. But in the end, all these logs from the agents are very different. They are not tamper evident, they are not authentic, they're just there. And then at some point they disappear, but for regulation you need them, right? So there's this nice guy on the right side. It's like, huh? It's just a very current state at the moment. So we want to improve a little bit on that, and that is what the IETF is for, interoperability and all these schemas and the things. So we have this mouthful of things. So we have the agent sessions. I was talking about that. They give us a lot. They give the message. They have some records of this. The tool calls. There's a lot of things they sometimes fetch from the internet and then ignore the robots.txt or whatever. And then everything happens. So we press all these heterogeneous agent-specific stuff into a CDL schema. We put that into a cozy sign-1. That's surprising because all of this is JSON, but it can't stay for long. JSON because it's very big, you want to be a little bit too concise, maybe there's a transformation thing there. At the end, you want to make this auditable. So we put this in a transparency log. That's work done, and at the IETF, it's basically concluded. So, and then we hope with some technical support, the auditor's happy now, because it has all the things after the fact. But also, we could do this live. There's this thing called the Security Event and Information Management System, and they process pattern analysis at a vast speed already. So maybe this is also an input to a live analysis system to stop things from happening before they derail scheme or break some railguards. But I think the most important thing is to have the conformity and the uniformity and the standards. So at the bottom, you can see that there's a compliance reliance mapping. We use it as formation model, and there's an internet draft, which is hard to read, but it's basically the name on the top. And we have a GitHub implementation to sign everything and write to use. So my ask is just have a time, take a peek, look at it, tell us where we're wrong, because at the moment, we are not, for example, retaining the original source of truth. This is the actual thing generated by the agent. Maybe that should also be authentic and a provenance path to the unified thing. But ideally, this isn't that bad. And this is a 0-0, to be honest, and it's a good 0-0, I think. But ideally, this could be the standard that we are going towards for every agent to use, and then we lose a lot of the complexity, and that would be so great, right? So look at it. Thank you. Right on time, huh?
All right, we're doing okay, but the applause has got a little softer over time, so maybe next time we'll ramp it back up again. Does the end-to-end argument still matter? We'll find out.
Hello, I'm Carlos from the Federal University of ABC, Brazil, and today I'm talking about the end-to-end argument, a principle that shaped the internet architecture for decades. And I have a simple question. Is it dead? The concept is very simple. The intelligence at the endpoints, a simple network in the middle, and the application semantics outside the network. However, at a certain point, we started to introduce middle boxes, firewalls, NATs, proxies, CDNs. And then at a certain point, the network basically said, hasta la vista, end-to-end. And today we're witnessing something new, because with this IoT, Internet of Things, we have like a continuum of processing stages from devices to the cloud, where data is filtered, aggregated, processed, interpreted, analyzed. So the semantics of the application are partially migrating inside the network. And to better design these applications, we developed IoT architectures. This is an example of a 5-layer IoT architecture. And multiple applications with multiple services. They have the services in certain layers of the architecture that must be mapped inside the stages of the continuum to do the deployment. And there are multiple ways of doing that. This is an example of agriculture for smart irrigation. We actually implemented this. And here the multiple services that compose this application. Considering the networking architecture, the OSI layers, you see that at a certain point, like for LoRa, there are no IP, and for others, you have multiple end-to-end connections, multiple point-to-point connections along the path, And where does it break? In multiple places, inside the network. So the question is, does this continuum erode the end-to-end? Yeah, the original end-to-end, it does erode. Is it good, bad, or ugly, or even somewhat else? But then, if you consider this networking end-to-end argument that goes multiples ups and downs, ups and downs, ups and downs, obviously it's broken. But then maybe we should consider a new end-to-end based on the IoT architecture, that the endpoints are different and maybe they are upside down. And this is the view of the continuum from the end-to-end data path. So I believe that the end-to-end arguments still matter. And I'm looking for collaborators to develop the ideas and eventually write an internet draft. If you feel like collaborating, please drop me an email. And thank you very much.
Yeah, that's more like it.
Good evening. I'm Daniel Huang from ZTE Corporation, and I'm going to talk about the high performance transmission over shared and public networks, which we would like to call it the HP1. And we'd like to define HP1 as the type of wide area network designed specifically to meet the high speed, no latency, and the high capacity needs for scientific research, education, and data-intensive applications. As far as the scope is concerned, contrary to the dedicated networking, we are going to focus on the public and shared network. That's why we call the HP1 wide area network. Our requirements is simply about the multi-petabyte the data transmission across the wide area networks, which demands the high throughput, no latency, high reliability within a designated completion time. We are talking about the problem of the existing mechanisms, such as congestion control algorithms, such as BBR and cubic, as well as the transport-related technologies, such as RDMA, IWAP, and RoCE2, may not be sufficient facing the challenges such as the poor convergence speed, unscheduled traffic, long feedback loops, and something like that. And here's the HP1 framework. It's designed to enable the hosted network the collaboration, and particularly enhances the congestion control and facilitates the functionalities for the hosted collaborative with the network to perform the rate negotiation between the hosted network, such as quota-based resource reservation, admission control, and traffic scheduling. So we will put a specific mechanism in place, such as the maximum transmit rate, which is designed to guarantee the avoidance of the congestion, and the minimum transmission rate is put in place to guarantee the designated completion time. And actually, we have made the hackathon in Shenzhen meeting, and here's the prototyping results. We have end-to-end solution, and we set up the testing environment with our partners, and we do some simulation on the topology for the public networks. And we focused on some service scenarios based on the HP1 framework and the related functions, such as the rate negotiation, admin control, and traffic scheduling. And we do the prototyping with the RSVP-TE extension. And here's some results I'd like to share. We employed RSVP signaling with the rate negotiation of the minimum and the maximum transmission rates between the host and the network. We can see from the second to third figure, the traditional seesaw effect from the transport algorithms, which contributes to the unreliability and the instability of the notch data transmission over the network. Well, under the HP1 prototyping, actually we can see the seesaw effect that has been largely flattened out. Yeah, that's all. Any comments and suggestions are welcome. Please feel free to reach out to me as well. We also have HP1 mailing list. Thank you. That's all.
Okay, which way is? Hello, I'm Micke Nordin. I'm with SUNET, and I'm going to talk to you a little bit about recent developments for Open Cloud Mesh. So Open Cloud Mesh is a server-to-server federation protocol across administrative domains. That means that you, as a user on System A, can share files or applications or other things with a user on System B without moving the resource or requiring a login on System A. So OCM works on the coordination layer, but the actual access is delegated to the protocols beneath, such as WebDAV or other things. It was adopted by the IETF OCM working group in November 2025, and the current active working group draft is 3 that we published in February. So we came in with a open API specification, which was rewritten in an IETF Internet Craft style in 1.2.0. And then we have added different features. So we have the .well-known OCM discovery point. We have requirements and tokens. We have added a directory service concept. We have a way of discovering servers. And we have formalized things such as how does an invite string look and how do you pass information between the systems. So the most recent specification has added more things such as an object model with functions and roles to make it easier to architecture a new implementation. We have added SSH or SFTP as a share access method. We have removed the older data transfer protocol in favor of an access type, so you can now use different transports for different access types. And we have cleaned up the token exchange so it is more in line with OAuth. And we have also modernized the message signatures that we use in line with HTTP message signatures, RFC 9421. Yes. So we are currently working on adding a resource discovery and request for share. So if you know that a resource exists, you can request access to that resource without somebody giving it to you. So it allows you to advertise data sets and things like that. So we are looking for people to review our draft, especially if you're focused on security. That would be great. Come and talk to us. We have a mailing list, ocm@ietf.org. And we have a GitHub, and you can read the draft in the data tracker. That's it for me. Thank you.
All right.
Okay, hello everyone. I'm Yu Jia from Zhuguangcun Lab, and the topic of the HOTRFC is about the feedback optimization framework for BGP flow spec. The BGP flow spec is widely used in carrier network for traffic handling or the DDoS attack mitigation, but the recent flow spec only provides one-way control where the successful rule propagation does not imply effective enforcement. So the flow spec rule may become ineffective due to policy conflicts, installation failures, or lack of traffic matching, and many persist without timely resolution. And for the control plan, operator may find the information through the flow spec routing table, but in the data plan, the enforcement results are not visible. So we think the operators
need execution feedback to understand the real enforcement behavior and continuously optimize the traffic handling strategies. So we propose a feedback optimization framework for BGP flow spec. The framework contains 3 layers, which are the intent plan, control plan, and data plan. And for each flow spec route, it may carry a feedback identifier. Upon the device receive the roles, it may confirm the status and update the state machine, and also configure the telemetry protocol. And then the router can use the telemetry protocol to report route installation status and also periodically send hit statistics collected from the data plan. To achieve this framework, it may have a lot of extension of the existing protocol, such as the definition of the state machine and the flow spec extension of the feedback action and the payload filter. And also we need to extension the existing telemetry protocol. Here is the definition of the state machine of this framework. We give different status such as idle, received, or the active or effective. It contains a life circle of flow spec rules, and people can check the status through this machine. And here is the feedback action we proposed in IDR working group. It's encoded in the community container and help the routers to check the definition of the feedback function. And we will introduce in detail on the Friday's IDR's meeting. And in the future, we are hoping to gather the community feedback to optimize the framework, and also looking for the collaborators and the suitable deployment scenarios. And also, we will propose a telemetry extension protocol. If anyone interested in this topic, please feel free to contact me, and I will on this meeting during this week. Thank you.
Nice picture.
So, yeah, my name is Christian Giese. I'm an access protocol engineer at RTBRIC, responsible for all the protocols that have to deal with access line attributes like PPPoE, DHCP v4, v6, LTTP, and radius. And therefore, I would like to get a bit more order into the attribute chaos we have today. So access line attributes are separated into identification attributes, like agent remote and circuit ID. Most of you know this as DHCP option 82, but they are also used in other protocols like PPPoE and radius. And there are characterization attributes like actual data rate up and downstream, and or min and max rates or DSL types. And these attributes are very useful in the DSL time because of the dynamics of the bandwidths, but still in the fiber world they are very important, and they become more important since more and more countries do open access, share their networks, and these attributes can pass network boundaries. So the problem here is that all the attributes are defined in multiple RFCs, even in expired drafts, but used in production, in program forum technical reports, and across all the protocols we use the same number space, which means that if we define a new attribute in ANCP, we use the same attribute also in PPPoE and radius without explicitly documenting this. This causes a lot of problems because as a user as well as a vendor, you have to first figure out what attributes are all defined going across all the standards, creating your own merged list of attributes defined across everything. And you have the high risk of having number conflicts, as we already had before. And another problem is that since we have a mix of broadband forum and IETF drafts in IANA, we have one number space, which is at the same time managed in the IANA and managed in the Podman forum, also causing lots of troubles here if you would like to add new attributes. And in the process of defining new attributes, we had already a number conflict in the last updates. And yeah, I would like to get a bit more order into this. So I'm really looking for people also impacted by this or interested in this topic, or vendors implementing or having the same troubles with access line attributes. I would like to ensure that all the attributes which are currently in use in production networks are reserved, which is not the state today. So I'm very happy that IANA has a booth here. And I plan to work on a draft doing a final overview of all the attributes from all the different documents into one single draft, explaining the usage of the access line attributes across all the protocols, because they are defined fragmented, but they are used transitive, so sent from PPPoE to L2TP and from L2TP to radius. So we need one document defining all the attributes and how they are mapped between the protocols, instead of forcing everybody to lead and merge all the documents. And yeah, this is what I plan. And if you are interested in this topic, just reach out to me. You can find me with my mail address, or you can see me here around. So.
All right, thank you. Our next speaker is remote.
Yeah, hello everyone. Oh, I hear a lot of echo. Should I start?
Yes, please, go ahead.
Okay, I'm hearing a lot of echo. Anyway, so welcome everyone. I'm Osama from TU Dresden. And next slide, please. I'm going to talk about how to, what ways, oh no, actually this one, yes, thanks. So I'm going to talk about how in TLS we can incorporate attestation. There are three main ways in which we can do that. And before I go there, so there is a motivation is that, for example, if the TLS key is leaked, then all of the security argument for TLS breaks. That's the thing that basically protects all of the security arguments there. And in order to protect that better, we have these trusted execution environments and a process of attestation. And there are now three ways in which we can extend TLS protocol with remote attestation to provide the two roots of trust, such that if the TLS key is leaked, the other one protects it. If the other one, that is the remote attestation key, leaks, then the TLS key will still protect us. So that's the kind of the complementary guarantee that we need from attested TLS. And in order to achieve that, three different approaches have been proposed. Pre-handshake, meaning that before starting the TLS handshake protocol, attestation or the evidence is signed already. Intra, meaning that that is done between the handshake protocol, and post, meaning it's done after the TLS protocol, TLS handshake protocol. So we did a formal analysis of the intra handshake attestation back in January last year. We reported to TLS protocol, hey, actually there are diversion attacks in the protocol that was proposed for SATI TLS attestation. And then by the end of the last year, that was already exploited in a number of ways. So I have slides forward next. But on the relay attacks, then we did some work on the relay attacks, that meaning that if there is some adversary in between, it can get some data from a malicious endpoint and forward it over to a genuine attester, and get back a genuine evidence and show it as its own. And by that, it can actually do the man-in-the-middle attack, or the relay attack, as we call it. So the proposal we have is to use post-handshake attestation, which is this draft SATI seat expat. And basically, it's based on simply RFC 9261, which is the exported authenticators, and it sends the certificate message with the CMW extension, which is the conceptual message wrapper in which you can add that evidence. And with that, it can just use that and build the security argument that is used for RFC 9261. Next slide, please. So these are the diversion attacks that I said they are practically exploited, battering RAM, wiretap.fail, and more recently like TE.fail, that's the DDR5. So all of these practical attacks are practical and only $5 to $10. So anyone can do that. There is no magic that you actually need to do that. Next slide, please. The second and more recent one I talked about for intra-handshake attacks were the relay attacks. And basically, this link will lead you to Cocos AI, who claim to be the best in the world, that we have designed such a secure protocol that nobody can break it. And we were the first to actually show them that this protocol they have designed is actually a broken one. And they have publicly acknowledged it. Our email, which we sent over to the seat mailing list, roughly like just rephrasing all of the things that we have said in that email. So basically, they are acknowledging all of that, the attacks that we pointed out. Next, please. So we are looking for implementers to implement our post-handshake attestation. We are looking for contributors to contribute to the formal analysis we are doing in ProVerif, but we would love to have other tools being used as well. And we are looking for collaborators knowledgeable in TLS, remote attestation, form methods, and confidential computing. Next, please. So these are the references. And next, please. A lot of people have contributed to it as authors, and as well as, next, please, as well as the contributors. Thanks a lot, everyone.
All right, we're back on the AI. All aboard. Last train out of the station. Go for it.
Hello, everybody. I'm Yaroslav. I'm Brian. And two of other co-authors, they chickened out. They decided not to travel to China. So today we would like to give you an exclusive preview of session that we're going to present tomorrow at Dispatch. So the draft that we've put together is about AI identity. So we believe that there is tendency to invent new AI protocols quite often without good reason, and we have decades of reasoning about identity, authentication, and authorization of things. And these standards that we've been building, they do apply to agentic AI in the very same way they do apply to workloads and many other stuff that we are used to be working with. So we are looking to build a framework document that would guide implementers to use the right set of standards when they reason with AI identity, authentication, authorization. We may find missing pieces in existing standards that we would need to surgically address, but we, with our framework, we believe that we don't need to build something dramatically new.
And as Yaroslav has said many times, one of the major aha moments through all this is that agents are in fact workloads. And they can be represented as workloads and authenticated as workloads.
Right. So there are building blocks that we identify in our draft. There are identifiers that we need to have in order to identify individual agentic workloads. They have certain credentials that need to be formatted. They need to carry some kind of attestation evidence. They need to be provisioned. They need to be able to authenticate themselves too when they speak to external things. They need to have authorization, and of course, human in the loop is a very important aspect of it. And they need to be observable, and they need to be monitored. So we would need to be able to go back and see what did go wrong and how can we make sure that it doesn't happen again. So there are a few key standard building blocks, and vast majority of them actually belong in IETF. So there is WIMC for identifiers, for credentials, authentication, authorization. There is OAuth with its avalanche of different standards for authorization and delegations that fit really well, surprisingly well, into this whole agentic AI thing. And there are OpenID foundation-based set of standards for monitoring and observability that also fit quite well here.
And with that, the outcome we're looking for here is for folks to come to Dispatch tomorrow and hear us basically go through the same presentation. And please contact Yaroslav for.
All right, thank you.
Oh, yeah. Good evening, everyone. So I'm here on behalf of my colleagues from Huawei, and we are exploring a practical deployment solution for remote attestation, and we are looking for collaborators to work with. So the background is that, so in practice, remote attestation often happens across domains. And in each domain, usually it has its separate remote attestation servers or services, and it will have its own policies and separate verify inputs. And this will create like two recurring problems. The first problem is cross-domain attestation transparency, because one RFC from one domain may need attestation artifacts such as endorsements or reference values from another domain. And on the other hand, many verifiers may need to collect those attestation artifacts from multiple endorsers or multiple reference value providers. And those endorsers and providers need to further distribute those artifacts to multiple verifiers. So this brings the need for a public mechanism where we could have those attestation artifacts produced, distributed, and reused in an effective manner. So this is the problem we are trying to solve. That is a scaling problem if we don't have this kind of publication mechanism. So to solve that problem, we have the first architecture, that is to have a distributed ledger publication with off-chain attestation and verification. And in this architecture, the attestation flow and verification flow are largely follow the existing routes architecture, while we have the endorsement and reference values published to the distributed ledger. So very simply, we will have reference value providers and endorsers to publish those artifacts onto the distributed ledger or the remote attestation service. The verifier or another authorized entity would issue a freshness challenge to the attester. Then the attester would send such attester evidence back to the verifier. The verifier would further fetch the inputs such as those shared reference values already stored on the distributed ledger to be able to evaluate the attestation evidence and produce non-attestation result. And such result could be used by a verifier or another relying party on their policy. And another architecture we developed is to have distributed ledger publication with optional on-chain verification. So the difference between this architecture with the first architecture we discussed is that the distributed ledger would further host registration logic or verification logic, for example, through smart contracts. So the first step or the zero step would be similar. So the reference value providers and endorsers will publish their artifacts onto the distributed ledger, maybe through registered smart contracts. And the distributed ledger would do verification on-chain through verification smart contract. And that relying party or verifier could obtain such result for deletion. We also have this whole process implemented. And if you are interested, please come to discuss more details or how to implement it in a more scalable way. Thank you.
That was our last speaker. Can we please have one more round of applause for all the speakers today? Thank you. Just a reminder, if there was anything you were interested in tonight, you didn't have to take notes. All of the slides are available in the data tracker. You can go through there, extract everyone's email addresses. You can run an LLM over the whole thing and try and figure out what we should actually do. Please prepare your ideas for HOTRFC next time in Vienna, IETF 126. See you there. Have a great evening.
上次都讲过了，你从哪瑞士过来吗？哦，是吗？哦，那你好好休息。你住哪里啊？还在我这一周度的。我们也在那儿。哎呀，我跟你说，这个智能授权的时候，好几个啊。对，我们现在就是你看这个这会啊，我就给他一个链接，我说，然后告诉他一把这个题的总结一下，发来一个。对吧 ？AI 我们就是你要真的把它打造成能用的报告，你还要用的把那些不好的完全在下面。没有，他那个做不了一个专项，但是呢，他一些总结性的工作，翻译可以做得好。好，那你早点回去休息啊，明儿见。直接找个地方拿，我也不知道。